In our discussions of interactions between the system and the surroundings, we have emphasized the surroundings' effect on the system by means of the force on the system due to something in the surroundings. The word interaction, though, implies that, in fact, the system can also have an impact on the surroundings. That's what we're going to discuss in today's lecture. Let's start with a specific example that we covered earlier. The gravitational force on our system, mass m2, due to an object, m1, in the surroundings. We discussed how Newton's gravitational law describes the force on m2 due to m1. Imagine now, however, that we made a different choice of system at the start. We're free to do that as we're responsible for deciding what we're choosing as our system and what belongs in the surroundings. So, here, we could have chosen the mass m1 as our system, in which case mass m2 would be in the surroundings. Newton's gravitational law applies here, whereby m1 experiences an attractive force, a force directed toward the object in the surroundings. And that force is directed along the line between the system and the surroundings. Let's give this force a symbol, F sub g on 1 by 2, which is shorthand for the gravitational force on mass 1 due to mass 2. We could then carry out the same thought process we used earlier, and we would end up finding that the magnitude of F sub g on 1 by 2 is given by a familiar expression, the universal gravitational constant, big G, times the product of the masses divided by the square of the distance between the masses, which, as we discussed earlier, this entire expression for the magnitude is the same as the magnitude of F sub g on 2 by 1. Now here we're combining results from thinking about the same physical situation using two different choices of system and surroundings. The use of multiple choices of system is often helpful to us to think through the physics of a given situation. We will be using more frequently this approach as we go on in the course. Here, though, what we learn is that the gravitational interaction exhibits a kind of symmetry. The gravitational force that m1 exerts on m2 is the same magnitude as the gravitational force that m2 exerts on m1. The directions of these two forces are not the same, but they are related. The direction of one force is flipped with respect to the other. Now, an interaction that exhibits these characteristics is said to exhibit reciprocity, which more popularly is known as Newton's third law. Now, in popular jargon, reciprocity or Newton's third law is often stated as, for every action, there is an equal and opposite reaction, which we now can see really means that a given force is associated with another force, and these forces are equal in magnitude but have directions that are flipped with respect to one another. Now, gravitational interactions are not alone in exhibiting reciprocity. The electric force, or more properly, the electrostatic force, which we discussed earlier, which is described by Coulomb's law, also exhibits reciprocity. Moreover, since many forces are fundamentally due to either gravitational or electric interactions, some forces we have discussed already, such as the weight and spring force, and some which we have yet to discuss a little later, all exhibit reciprocity, which makes the concept of reciprocity something that we often can use to help us understand a variety of force and motion situations. We will have ample opportunities to apply reciprocity in such cases a little later in the course. Before we do that, let's try this question. Since we are given the mass of the person, we use knowledge of g, the strength of the gravitational field near the Earth's surface, to find the magnitude of the weight force on the person. Or, more explicitly, since the weight force is just the gravitational force on the person by the Earth, then by Newton's third law, reciprocity tells us that the magnitude of the weight force must also be equal to the magnitude of the gravitational force on the Earth by the person. It may seem peculiar that objects of such very different size, like the Earth and a person, can exert the same magnitude of gravitational force on each other, but that's what reciprocity says. Now, here, let's be careful to note that just because the Earth and the person experience the same magnitude of gravitational force does not mean that this gravitational force has the same effect on each object. Say, for example, the same effect on each object's motion. Newton's third law does not address this issue. That's not the job of Newton's third law. It's the job of Newton's second law, one of our fundamental principles, to tell us something about whether or not the gravitational interaction on one or the other of these objects can, in fact, affect that object's motion.